So let's talk a little bit about Flux environments. Where can I run Flux? Oh, hey, Fluxbird. How's it going? So for people that haven't met Fluxbird, Fluxbird is the pink bird that knows things, and he knows quite a bit. So Fluxbird thinks there's only one way to answer that question, and I think I know where that's going. Fluxbird really likes poetry. Let's do this. You can run it on a cluster. You can run it alongside Lustre. You can run it on a share. You can run it anywhere. You can run it in a container. Flux is a portability layer. Thank you, Fluxbird. That was excellent poetry. So to kind of put this into terms that the audience can better understand, here's a list of all the places you might want to run Flux. And Flux does not care where you're running it. It sees the system resource the same. So we have the system level scheduler of an HPC system, such as LCAP. We have in user space, actually under another scheduler like Slurm, or in user space Kubernetes, actually alongside of it. That's a turducken that we don't have to go into. We can run it as a single Docker container or as a set of orchestrated containers, a full Flux cluster in Kubernetes, or on virtual machines. And so we're briefly going to go through some of these setups today, along with some of the work that we're doing on the various setups. So Fluxbird is asking, why do we need this portability? And I think that's a really good question to go into before we go into all these environments, because arguably you could just have one of the environments in this list, such as the first one, your HPC system, and just forget the rest. So why do we need this, Fluxbird? Well, the reason is because if you look around the ecosystem recently, emerging workflows have become incredibly complex and heterogeneous. So what does that mean? It means they have a combination of AI, ML, and simulation components that need complex orchestration. So what you're looking at here is a workflow called MuMMI. MuMMI models cancer-causing protein interactions. This is a proxy app to it called Mini MuMMI. And just for a fun fact, the name MuMMI is a tip of the hat off to the Moomins, these cute little white hippo guys that were the stars of a book series from about 1945-ish into the early 90s. So let's talk about Mini MuMMI. The first thing we start with is the machine learning. So this is an ML server that is generating structures, sampling from a latent distributed space. When the structures are valid, it hands them off to the simulation. So the simulation has two components. The green is the create sims, which does exactly as it sounds. It sets up the simulation. That then hands off to CG analysis, the red, which actually runs the simulation. Now, all of this needs to be brought together with orchestration. That's your workflow manager. The production MuMMI initially used Maestro for a job adapter, and then that with Flux. You also need services, so there's a RabbitMQ to basically send messages between the workflow manager and the ML server like, hey, we need more samples. Right away, sir, right away, sir. So why didn't this work well? Well, it's not that it didn't work well, but why wasn't it optimal in terms of resource utilization with traditional HPC? The answer is because they struggle with orchestration. So in order to run MuMMI, a DAT was required to request all of the possible resources that MuMMI might need in its entirety of running time. And so what that meant, if you look in the plot to the right, is that there's an initial hour of ramp-up time where MuMMI couldn't use a large portion of the resources that it had allocated. So that means that the CPU were sitting around like, hey guys, didn't we sign up to like do science and great things, and I'm idle, I'm not doing anything. So if you look in the left, you'll see how this resource occupancy was in the pink. It's about 50% per CPU. We can do better. So let's step back and ask a question. What do we want the future to look like? And let's ask this question in terms of features. So the first thing that we want is portability. I should be able to have a workflow step and run it in environment A, and then seamlessly move it over to environment B. And I want to choose my environments based on where they're best suited to run. So that doesn't just mean resources, that also means cost and what is available to me. Because, for example, as we may know, GPUs are really hard to get in the cloud these days, but not as bad to get on premises. So for example, let's say you have your HPC system and you have your cloud, and you're running on the HPC and you're like, oh man, that API that we use in that cloud service, it was so great. You should be able to very easily transition over, hop over your work to use the cloud service. So you're on the cloud service and you're like, oh gosh, darn, GPUs are really hard to get here. Let's go back to the on-premises cluster. So the point here is that we just need to be portable. We need our workflows to be able to move seamlessly between the spaces. And the insight that we've had recently is that portability is a metric of performance. You could spend 6 months to a year with your team optimizing a single application for one environment to get it to run perfectly. But what if you could take the same team, spend 3 months, so like half the time, to get it running in 4 environments, maybe not perfectly, but maybe very good. And maybe then you might get it done faster or more cheaply. And so this is a new trade-off that teams are now having to increasingly consider. The next feature that we want is elasticity. And this is exactly what it sounds like. We want to scale up and we want to scale down based on what your workflow needs. So here is kind of a static picture of resource needs through time. You can imagine a workflow like MuMMI might need GPUs at some time, might need CPUs, and that goes up and down. And so the problem with running on a traditional HPC allocation is that because it's this static block, you have a lot of unused capacity. So we'd want to be able to auto scale up and down. The final thing is dynamism. You want your orchestration tool to respond to state. So when you have a traditional DAG, a directed acyclic graph, which is the most common representation of a workflow, you cannot account for uncertainty and loops. So for example, let's say you're sampling from a model and it fails, which happens quite a bit. You would ideally like to adjust the parameters and keep trying until you get that correct sample that can move on to the simulation. And so this is a design that looks more like a state machine, something that we're going to be talking about. Okay, let's jump into the environments. We are going to start with one of my favorite things, containers. So a really easy, great approach to getting started with Flux, if you've never looked at it before, is to run a container. And so when you Docker run Flux RM, Flux Resource Manager, Flux Sched Jammy, you basically have Flux, just like that. So you do Flux Resource List, that shows you the resources, and you can do Flux run whatever. Everyone always chooses host name or sleep or echo, and so we echo the host name and there's the Docker container. It really is that easy. This is an amazing environment for just learning Flux, getting started, testing random stuff, checking output. I use this all the time, even years later. Now, if you want to kind of increase the number of containers that you have, we have the equivalent idea, but with Docker Compose. So of course, Docker Compose upd, you generate some number of nodes, and then you have actual nodes there, but they're containers. Now, the reason that I don't use this one as much is because with the single Docker container, you can do a Flux start with the flag test size. And that's actually going to create you 4 nodes that are kind of simulated fake nodes. It doesn't mean that you have more cores on your computer. Don't overwhelm your single little portable computer's resources, but it does mean that you can test without needing, for example, Docker Compose. Okay, let's jump into my favorite environment. That is Kubernetes. It's like an extension of the container landscape. We have the Flux Operator. The Flux Operator is going to deploy the entirety of Flux framework, a Flux mini cluster in Kubernetes. We designed this by basically taking our Flux components, mapping them into Kubernetes abstractions, and then the operator is this controller, like a program that works in Kubernetes that knows how to manage all of those objects. So for example, if your cluster is going to scale up and down in size, so your operator endpoint for scale knows how to handle that. So here's what it looks like. You start with a CRD, a custom resource definition. You say, I want this container and this command, and I want this size. Your container does not need to have Flux in it. Flux will be added on the fly via a view. So then the operator is going to do what's called reconcile. This is its main function. So the idea is that it's going to look at what you asked for, look at the state of the cluster, and be like, these things are not the same. I am going to keep making incremental changes until they are the same. And then poof, once it's done and the states are equal, you get your full Flux mini cluster. This has a leader with some number of follower brokers, and they have a T-bone, the tree-based overlay network, and that's what you see here in purple. And so this also has different execution modes, so you can kind of run work, or you can shell in interactively. And did you know this tool has enabled so much cool work, and I will leave it at that. I love using the Flux Operator. So here is what that interaction that I just described looks like for the interactive case. In this case, we created our cluster with Kind, Kubernetes, and Docker. We applied our YAML file, we shelled in, we ran a few commands to connect to the lead broker, and then boom, there we have our Flux. And these are, again, are not real nodes because this is Kind, but these could be real nodes in the cloud if you use a cloud deployment. Now, some recent work that we're really excited about is we had this vision where we want to have many different HPC applications that are just available and ready to use. So we use something called Helm. Helm is technically a templating engine, but people in the cloud community sometimes call it a package manager. Not really a package manager, but most big projects use it to easily deploy their stuff. And so the basic idea is that we build containers for many applications. We have about 30 at this point. Some of them are listed to the right. And then you have what are called Helm charts. And we basically expose in these charts the variables for not just the cluster, but also the application. So you're looking at AMG on the left of the screen here, and you see that you deploy the entire experiment. So not just running AMG once, but running numbers of iterations of it and saving the output files, everything that you need. One copy-paste command. This has made our lives so much easier, and we're very excited about sharing this work, which is being drafted at the moment. The other really exciting thing about this particular setup is that we're getting into eBPF, the extended Berkeley Packet Filter. So here is that diagram of the Flux operator that we kind of saw before, but here's a cool component. So we have now a sidecar container, and actually the Flux operator can deploy any sidecar container. This particular one is running a particular container that has a bunch of eBPF programs in it. So an eBPF program is basically going to be a program that uses hooks into the kernel and other different strategies to basically have a very low overhead way of monitoring what your application is doing. Because there's a shared process space between this container and your application container, it sees everything that's going on. And so we've done a bunch of work to basically look at metrics across CPU and futexes and shared memory and file opens and closes and everything we could think of for this early study to look at this as a potential means to do performance assessment in Kubernetes for HPC applications and beyond. I'm just kidding. So here's the example command, sorry, the little example flag that you just have to add. For all of that to happen, I don't have time today to go into the details of how to get eBPF working in a container Kubernetes, but for you, the user, you add that one set experiment monitor equals these things, and you are done. So hopefully I'll be talking about this at a future talk. Alrighty, so I alluded to this. Some other work we've been doing is modeling MuMMI as a state machine with Event Driven Orchestration. What does this mean? It means that instead of this DAG, this static DAG that's like keep going until you hit error and then die, it's basically we have workflows that are goal-oriented. So what does that mean? It means that we create a state machine manager that's running in Kubernetes. It will be in a pod. On bare metal, it would be sort of a process. And either the state machine manager is going to be receiving events from Flux or Kubernetes. And the really cool part is because those are both event-driven, you can run the same workflows with Flux or with Kubernetes, and you're just swapping out that particular backend. And so that's what we've done in this early work. What it means going through the steps is that we create a definition of our state machine. The jobs, the workflow parameters, that's where the goals are. So I want this number of completions. The orchestration logic, like don't go above this maximum cluster size because my credit card cannot handle it. That then creates this manager we talked about. And then each job is actually modeled as a state machine. So a sequence of these steps is one state machine. This is fundamentally different from the initial MuMMI design, which had one job manager watching all of the machine learning jobs, all of the Kratzen's job. And that's really cool because it allows each state machine to act independently. That creates some step, maybe it'll fail a million times and it's okay. It's not going to interfere with other state machines that have a different outcome. The other really awesome thing we can do with this state machine library and operator that we've made is basically have logic in our workflow that are based on metrics. For example, here is using PyTorch, and the idea is that we want to keep training a model until we reach this metric of goodness. And so each of the colored boxes here is a job. And what you're basically seeing is we had rules that said, keep going until you hit 70% accuracy. So what we see here with the fifth job, that's the gray box, is that's when we hit 70%. That's when it ended. And here's what that YAML file looked like. You can see the events. When the max PyTorch accuracy is greater than or equal to 0.7, finish. When it's less than 0.7, repeat, and keep repeating. And hopefully that's a good decision. And then for the user, when you want to actually get the metric, you just write a little snippet in Python with regular expressions. I really like writing regular expressions. And you basically just return a dictionary of the metrics that are relevant that we reference in this particular section here. Alrighty, so how does this actually improve upon time to completion and cost? So this is time to completion. What you're seeing is different environments that we ran it on for each of CPU and GPU and the workflow total completion time. So this first one, this is Flux running with the state machine orchestration. This is the state machine operator running in Kubernetes with auto scaling. This is the same thing without auto scaling. So it makes sense those times to complete are about the same because we're just removing nodes at the end that we're not using. This is actually MuMMI in Kubernetes that we implemented to have still the traditional MuMMI design just in Kubernetes. So it would be a closer comparison to the state machine operator. And this is like very much traditional on-premises MuMMI. That's why we only have GPU, because we don't have like a CPU-only cluster that we usually run it on. Now, very importantly, this white line is the theoretical best time. We calculated this based on summing up all of the jobs that have to run. So this would be the time that the workflow would take if you removed all the orchestration. So that white line being closer to the top of the bar is better because it means that there's lower overhead. So what do we see? We see that the lowest overhead has to do with the state machine designs. In terms of the total workflow completion time, Flux was the leader, and then the different state machine setups. But you're probably wondering about costs. And so the biggest surprise here wasn't necessarily, the state machine or not. Like the state machine generally had a lower cost than MuMMI. The big surprise here was CPU versus GPU. So we found that an instance in Amazon, the AWS Graviton HPC 7G, which is an ARM instance, just worked really well for this particular steps in this workflow. And so we need to do more kind of looking into why that was, and as opposed to GPU. But that was a very interesting finding. Now, the next thing that we might be interested in, let's say before you run your workflow, you want to know which instance to choose, period. And we had this exact question. So you can actually design a state machine workflow that says, like, let's add auto scaling to this. So now give me the instance, the exact instance that I want to run the same steps, so the same container with the same data across these instance types. And then save some metric of goodness for the simulation. So this was, we calculated cost per simulation nanoseconds. And as you can see, what we found is that between on-demand and spot for all these instance types, the HPC 7G was really the best bang for the buck. And we chose on-demand because no one likes losing spot instances and no one likes waiting for spot instances. And yeah, I really like the HPC 7G. Okay, let's move into back to the cloud. Actually, we never really left the cloud. And okay, we're going to talk about virtual machine setups. So all of our setups are builds with Packer, which is used to build the VMs, and we orchestrate with Terraform to infinity and beyond, actually just on my local machine. So the first one in AWS, we deploy to EC2. We use the Elastic Fabric Adapter, or EFA, and we use those HPC family of instances. So the HPC 7G, the 7A, and the 6A are the ones we've traditionally used. On Azure, we deploy it as a VM set. We use InfiniBand Fabric, and at the time we made it, we used the standard HB120v3. I believe we're a few generations later than that because we cannot keep up with the generations of these instance types. And finally, on Compute Engine, we use Tier 1 networking, and you could also use one of their compute-optimized families with the Titanium microcontrollers. Alrighty, that's for last. Traditional HPC. You're probably like, why is she not talking about the most obvious answer to this question? Just hang on. Okay, so we obviously have Flux running as the system-level scheduler. Here's just the list of systems from the top 500 where it is a system-level scheduler. Now, some of the really cool work that we actually have on premises with Flux is running user space Kubernetes alongside it. So this is the idea that we want the best of both worlds. Run your simulations on bare metal, run your services in Kubernetes, everyone's happy. And so we've done a couple of setups. We've done this in AWS using the Elastic Fabric Adapter. We've run it in Azure using InfiniBand. And our production on-premises clusters are like literally just getting created now. So we haven't done a lot of work, but we're still incredibly excited about it. So what is this interaction going to look like? We actually have implemented this, but we haven't tested it fully yet. The idea is that a user is going to request a batch job or allocation, and they're going to set an attribute on the job that's like, I want you to set up Kubernetes for me. And the idea is that the user space Kubernetes cluster is going to be brought up. it's going to be up for the life cycle of the allocation and then torn down. And then the really cool part is that when you're in the allocation, you can be like Flux resource list and you see your nodes as represented by Flux. And then you do kubectl get nodes and you see the exact same nodes, but from the view of Kubernetes. How does this design actually look? Well, here we have a set of 9 fake nodes, PowerPoint slide nodes is the best I could do. And the idea is that Flux is running on the system. And then for each of those nodes, we either have a kubelet running or the control plane. We deploy it with a rootless container technology. On our clusters, we have Podman. It's deployed with Docker Compose and a make file. Cluster configuration is done with kubeadm. The CRI is containerd. OCI is runc, and the CNI, the container network interface, is Flannel. And then this kind of a view that both Flux and Kubernetes have a view of the cluster from a networking perspective. Bro, high five, high five. So this project, as I said, is called the Bare Metal Bros because we believe Kubernetes and Flux really are kind of like friends like that. They're going to work very well together. Now, the way that, so one caveat here, Usernetes uses something called Slurp for NFS, for Slurp for NetNS. My apologies. It's right on the slide. I didn't have to remember it. And so this uses a tap device. So the packets have to go through this additional device and it really hurts performance. I mean, like it takes twice as long to run the same thing and it doesn't scale as well. But we can use a bypass mechanism, such as with EFA. So that's what's illustrated here, where the application might talk to libfabric, and then libfabric can talk directly to the devices instead. And with that, we get very similar performance. How similar? Well, we're going to get to that. Now, here's an example that I mentioned of what a workflow might look like when the bare metal bros are doing their broy thing. So you might be running simulations on bare metal, sending off data from some training application to a machine learning endpoint, which is running in user space Kubernetes. The server is training a model. And then on the other side, maybe when you have enough samples or reach some metric of goodness, you might then generate test data, ask that model or one or more models for prediction, get the actual versus the prediction, see how well you did, and then your job goes away and you're done, and it's really awesome. Going back now to the running it with EFA on AWS, this is what we saw across the scale. So you'll notice that the performance in terms of the duration of the job, this is lamps for a 16 by 16 by 8 problem size, it's very similar up to size 32. Then we start to see some overhead for Usernetes. We are still investigating that. The same is true for InfiniBand, maybe to a slightly less extent at the largest size. And then finally, the bare metal. This might be the worst result that I've ever presented. So we literally have just started this and we didn't have time to do more because we had to record these talks and whatnot. But basically, if we run lamps, so we brought up user space Kubernetes on one of our production clusters, which took a hot minute, might I tell you. And we can look at CPU utilization and the lamp's wall time for 1 and 2 nodes. So 1 wouldn't be utilizing the network and 2 would. And so the CPU utilization is very good on 1 node. The wall time is fairly low for 1 node. Once we increase the 2 nodes and we're using Slurp for NetNS, well, the CPU utilization is really bad. It looks like it's slightly below 60%. And then the wall time, it's actually I think it's about 4 times greater. Yeah, this result's terrible, but it's a really good starting point, and we are immensely excited to we're pretty sure that the InfiniBand is just going to work because we've tested it in other environments. We're going to add that InfiniBand, test it at other scales, and we will probably be talking about this at a future talk.